everyone, in this video we're going to be looking at rates of change in this calculus unit. So we've talked about the derivative and what the derivative does. One of the things that we need to understand about the derivative is it measures the slope of a curve, the slope of a tangent to a curve, the gradient of the curve, all of those things, but it also is the rate of change of the curve, the instantaneous rate of change. So when we examine this, we looked at a distance time graph, and we were talking about that the slope of the graph at any time was speed. That's the instantaneous rate of change, in that case, the speed. This can apply to other situations. So in this video we're just going to look at a few examples of that. So in this one here we've got p is equal to 5t squared plus 6t. Now these equations that we've got here may be modeling certain situations like population in terms of time, volume in terms of time, all kinds of things. So when we're talking about a rate of change, we're normally talking about with respect to time. So dv dt, this thing here, is the rate that the volume is changing with respect to time. I might have another variable like ds dt, might be the surface area. That's the rate the surface area is increasing with respect to time. So you'd expect these things here to be something like, litres per minute for the volume, or centimetres squared per second if we're talking about the rate of change of the surface area of a balloon. There's all kinds of cool relationships going on here with that calculus can help us understand. So here's some real basic examples. If p is equal to that, find an expression for the rate of change of p with respect to t. What that means is dp dt. So we're doing the derivative, but instead of y's and x's, we've got p's and t's here. So we're going to use the same rules. Number down the front, subtract 1 from the power, and for 6t the derivative is just 6. So remember, if we had 6x, the derivative was always just the number in front of the x. Remember, this is a straight line gradient 6, so the slope of this thing here is always a constant 6. Okay, so we've just changed the letters here basically. That's pretty easy. In this one here, find the rate of change of L with respect to A when A equals 3. So we want dL dA. That is the rate of change of L with respect to the variable A. So again, we're just going to use the same rules that we know how to do, and we get 3a squared minus 6a is the derivative, or the rate of change of L with respect to A. And the question asked us to find what that rate was when A was equal to 3. Okay, so we get 27 minus 18, which is 9. That's the rate of change at that exact time. So we're trying to model some real physical situation here. These derivatives are going to be really important, and this might be a profit that a company is making. We want to maximize our profit or minimize the cost or something like that. So mathematicians get a lot into coming up with equations that model certain situations. Okay, in example 3, the volume of a sphere is increased such a way that the volume is given by that equation there. So here we've got the volume of a sphere at time t. So when t is equal to 0 here, we can see the volume is 7,500 centimeters cubed. Okay, so that's 7.5 liters. There's 1,000 centimeters cubed in a liter, so 7.5 liters. So this is a big sphere to start with, and we want to see kind of what's going on as time goes on. So first calculation is easy. What's the volume when t is equal to 12? So we just need to substitute 12 in there, plus 3,600 times 12 minus 150 times 12 squared. Okay, so if you do that on your calculator, you should get that. So it's increased from the first time. Now you can see, because of this negative t squared thing, we're going to have a curve that does something like that. So we're going to start here at 7,500. It's going to go up for a while, it's going to reach a peak, and then it's going to come down again if we were to look at the graph of this function. Okay, B, an expression for the rate of change of the volume with respect to time. That is dv dt. That's the rate the volume is changing. Okay, so let's do the derivative. The derivative of 7500 is just 0. The derivative of 3600t is just 3600. And the derivative of negative 150t squared, bring the 2 down the front, subtract 1 from the power, so we get negative 300t. So that's the instantaneous rate of change of the volume. So when t is equal to 0, we can see what rate the volume is increasing at the exact instant t is equal to 0. When t equals 1, we can put it in there. You can see that the rate of change of the volume is always going down here. The greater value we make t, the smaller the rate of change of the volume is. And c, the rate at which the volume is increasing when t is equal to 2 and t is equal to 10. So all we have to do is substitute 2 into there, and when we do that, we get 3000. And the units here are important. That would be, because we're talking about volume, centimeters cubed per second. And the last one, minus 300 times 10. So that's only 600 centimeters cubed per second. Okay, so you can see it slowed right down. So there's some basic examples using calculus, rates of change using